for ocean optics is bioluminescence, where the chemical energy of reactions of certain molecules is being utilized to, or converted, if you wish, to produce photons, bioluminescent photons, and that this occurs in many marine organisms and microorganisms. But my focus will be primarily on thermal radiation today, the mechanism of thermal radiation, and one of the most relevant example of a thermal radiator is the sun itself. But as I indicated, all other bodies at temperatures higher than 0 Kelvin emit radiation. So atoms and molecules possess, can say, 4 types of energy. Energy associated with thermal motion is this is the type of kinetic energy where all atoms and molecules experience a motion, and depending on the temperature, the kinetic energy of this motion can be higher or lower. So in fact, the temperature is a measure of kinetic energy of atoms and molecules in this thermal motion. And this energy can be exchanged as a result of collisions between atoms and molecules, and it can be exchanged continuously. And there are 3 other forms of energy that are very important to consider, which are actually quantized. So in other words, they exist only in discrete amounts. Atoms can possess internal energies associated with the distribution of electrons. This is called electronic energy levels, different energy levels depending on where the electrons are and how they are distributed within the atoms, so orbital shells and so on and so forth. The second type of internal energy that is quantized is referred to as vibrational energy, and these discrete levels of vibration energy are associated with different modes of vibrations of atoms within molecules. And finally, the third form of internal energy that is also quantized is rotational energy, that is associated with the way the molecules rotate. And here in this graph, we have a schematic representation of a simple 2 energy level atom. These on the left-hand side or in the middle, you can see just 2 horizontal lines. They are supposed to represent internal energy levels of atoms. So for example, of the left-hand side, the lower horizontal line represents some lower internal energy level, and the higher, the thicker line represents some excited state, higher internal energy level. So for example, this could be an atom that is at the lowest electronic level, that is called ground level. Both these lines can be associated with the lowest electronic level, but these 2 lines may represent different internal vibrational energy levels. And so for example, at typical environmental temperatures, room temperatures, almost all atoms and molecules are actually in the ground electronic state, and the ground electronic state is defined rigorously as a state to which all atoms, molecules tend when the temperature approaches absolute 0. But in fact, at room temperature, the probability of finding atoms excited to higher electronic levels is extremely, extremely small. So, for example, when the thermal motion at room temperatures occurs, the atoms can collide and can exchange that energy and can excite. The atom can be, as a result of collisional exchange of energy, can be excited to higher vibrational level still within the lowest ground electronic level, and that's what's shown here. And then once this excited level is achieved, the fate of that excitation energy can be different in a sense that this excitation energy again can be quenched to the lower internal energy level, again through collisions with other surrounding atoms, or we can have an emission of photon that corresponds to this difference of internal energy levels. So in this case, if we are within the vibrational transitions at room temperature, this would be a photon emitted in infrared portion of the spectrum. But of course, if the bodies are hotter, higher temperatures, these two lines could represent different electronic levels. So very hot body, in a very hot body, the molecules can have very high kinetic energy of thermal motion, and upon collision, we can have excitation to higher electronic levels, and the fate of that excitation energy can be emission of photon, but now that photon would possess higher energy, shorter wavelength, can be indivisible. So hotter bodies can will emit radiation, and that can be visible. And other ways of changing internal energy, except for collisional excitation, are associated with radiative processes. So the photon incident upon the atom, the system, the two-level atom, a photon that possesses appropriate energy, appropriate in a sense that it corresponds exactly to this gap, to this difference between two internal energy levels, can be absorbed. And so as a result of absorption, the atom is excited to higher internal energy level that can be again vibrational, rotational, or electronic, depending on the actual energy of the incident photon and the match between the incident photon, energy of incident photon, and these differences in internal energy levels, rotational, vibrational, or electronic. And again, the fate of that excitation energy, it can be one of the pathways to go back to the lower energy level is emission of a photon. It can be spontaneous, but there are also phenomena associated with stimulated emission by an incident photon. So you can see here there is a variety of ways of excite. Several ways of excite atoms to higher internal energy levels. There are several types of these internal energy levels. And basically the process of emission is associated with the excitations from higher emission of photon is associated with the excitation from higher internal energy level to lower internal energy level. And the process of emission has been of bodies at different temperatures has been of great interest in physics in late 19th centuries, and the experimental observations of radiant energy being emitted by bodies of different temperatures could not be explained at the second half of 19th century, as we learned yesterday. The classical electromagnetic theory has been developed and is associated largely with Maxwell equations. But the radiation, thermal radiation, could not be explained using this classical electromagnetic theory. And so this was, in addition to photoelectric effect, which we discussed yesterday, which led to the concept of quantized nature of light in terms of photons, particle-like nature. Another concept associated with thermal radiation also required something more than just classical electromagnetic wave theory. And this concept has been pursued, or the attempt to understand thermal radiation has been pursued through a concept of idealized physical body referred to as black body. And this is a body that absorbed all incident electromagnetic radiation, regardless of frequency, wavelength, or angle of incidence. And an approximate realization of a black body is a cavity which has a small hole in the wall, and with walls that are opaque to the radiation. So we can see here the schematic diagram of a black body cavity with the small hole here. All radiant energy entering the black body is absorbed by atoms distributed along the walls, internal surface of the walls of the cavity, and in reverse, an aperture of a heated black body is also a source of thermal radiation emitted by black body. And for ideal black body in thermal equilibrium, that is when the temperature is constant, the emitted energy equals absorbed energy. So essentially what happens here, you can imagine very many atoms here distributed along the within the cavity, along the surface of the wall of the cavity, and the photons that interact with these atoms are absorbed and re-emitted, and these processes occur, all the time, and until and in thermal equilibrium, the absorption is balancing the emission. And the property of this black body radiation within cavity is that at every frequency and wavelength, it emits as much or more thermal radiative energy as any other body at the same temperature. That's the property of the black body. So not all bodies are black bodies, because some bodies can transmit or reflect radiation. They would be referred to as gray bodies. But this idealized concept is such that it emits as much or more thermal energy as any other body at the same temperature. It also possesses this thermal radiation of black body possesses characteristic of diffuse emitter. So the radiation is isotropic, independent of the direction. And this concept, although idealized, was very important, and because it provided a basis for theoretical explanation of thermal radiation, and this theoretical explanation has been provided by Max Planck in his work in 1901. So he has considered this cavity, the black body cavity, and atoms as he postulated that these atoms behave as sort of like mechanical oscillators, which have specific frequency of oscillations, and this frequency of oscillations correspond to quantized amount of energy that can be absorbed by these atoms or emitted, and they can only be absorbed and emitted in jumps. So in other words, in quantized discrete amounts, not continuously. So Planck was actually the first one to postulate the quantized nature of interaction of light and matter, but he himself in his publication indicated that he uses this concept solely. He sort of didn't pursue it to the point that he claimed that light has a quantized particle-like nature. He just used it as ancillary tool to explain observational facts about black body radiation. But nevertheless, Planck, for his work, did receive Nobel Prize in 1918. But Einstein, as I indicated yesterday, in 1905, actually postulated that light is quantized and exists in the form of particle-like discrete parcels of energy. And he received his Nobel Prize, I think, in 1921, and photoelectric effect was indicated in his Nobel Prize presentation as a major contribution to this prize. So here in the slide we have a formulation of Planck's radiation law. This is a very important physical law which determines the intensity of thermal radiant energy as a function of wavelength for any temperature of the body. And so you can see here on the left-hand side a graph where you see different lines, each corresponding to a different temperature in Kelvin, and they're plotted as a function of wavelength. So you can see here visible portion of the spectrum, and to the left you are going into UV, and to the right to longer portion of the spectrum, infrared. And on the right-hand side here of this, you can see the equation. There are several forms of Planck's radiation law. Here I have chosen to present the equation that represents on the left-hand side the quantity that is radiometric quantity that is called radiance. So it's an emitted radiance by a black body is essentially the energy per unit time, per unit area, per steradian, which is a measure of solid angle along the direction of consideration, and per unit wavelength interval, because this is a spectral quantity at a specific wavelength, but we always have some finite bandwidth around the nominal wavelength of interest. So you will learn more about radiometric quantities during this course. So radiance, of course, is one of the fundamental quantities in ocean optics. So here you can see that radiance of thermal emission is dependent on two variables, lambda and temperature, and everything else here, all other parameters are constant. So h is a Planck's constant, c is the phase velocity of light, and k sub b is the Boltzmann constant. And this equation, if you graph it, it takes the form of this curve, and you can see there are three main features that I would like to emphasize here. First, you can see that as the temperature of the body increases, the maximum emission is shifting towards shorter wavelengths. And the second important observation here is that as the temperature of body increases, we can see that the integral under Planck's curve is decreasing. So the total amount of emitted energy is strongly dependent on temperature of the body. And finally, you can see also here this red line, which connects the maxima of each curve for different temperatures. So it shows how the lambda peak, or lambda corresponding to the maximum of Planck curve, depends on temperature. So and the bottom line is here, okay, you can see that very hot bodies, the temperature 7,000, 6,000, 5,000 Kelvin, they peak in the visible spectral region. So there's a lot of radiation emitted in the visible. If we have bodies at much lower temperatures, you can see a lot more energy being emitted, by also the maximum is shifting towards longer wavelengths into the infrared. So that energy is not visible to the human eye. And there are two other laws that are can be directly derived from Planck's radiation law. The first one is Stefan Boltzmann law, which states that a black body emits electromagnetic radiations with a total energy flux proportional to the fourth power of the Kelvin temperature of the object. So that's indicated here. And in this case, on the left-hand side, we have a radiometric quantity referred to as irradiance rather than radiance. So it's energy per unit time per area. So it's now integrated over a range of spatial integration over a range of direction of propagation of light, as opposed to radiance, which is a directional quantity, is associated with specific direction of propagation of light. So very, very strong dependence of total energy of thermal emission on temperature. And finally, the Wien's displacement law, which can be derived also from Planck's law, but this law has been independently derived or formulated before even Planck formulated his law by Wilhelm Wien based on empirical data. And this law states that the dominant wavelength at which a black body emits electromagnetic radiation is inversely proportional to the Kelvin temperature of the object. So you see here this dependence of lambda maximum or lambda peak on the previous graph is inversely proportional to temperature. So this has a very important implications. For example, the sun has lambda maximum around 500 nanometers because the outer layer of the sun atmosphere, which is called photosphere, is at the temperature of about 6,000 Kelvin or maybe 5,800 Kelvin, something in that range. Human body at 37 degrees Celsius or 310 Kelvin emits radiation with a maximum at about 9,350 nanometers or 9.35 micron. Earth's surface at 15 degrees centigrade, which is about 288 Kelvin, has a maximum emission at about 10 microns. So you can see this dramatic difference. And then, of course, according to what we saw here, the total amount of energy will be very different for not only this lambda maximum is shifting dramatically, but of course the amount of energy emitted by hot bodies such as sun versus surface of the Earth will be dramatically different. So here's a schematic illustration of three examples of Planck's radiation curve for 6,000 Kelvin, which is more or less representative of the sun, fire, 1,000 Kelvin, or Earth surface, 300 Kelvin. So you can see all these features that I've just described here in these three curves, the change of lambda maximum, the decrease in the total amount of energy. And you can see that, of course, if sun peaks within the visible spectral region, we can see fire very easily because there's a lot of energy in the visible, although there's quite a lot in the infrared, but Earth emission is so low if we approach here the visible spectral region that we can't see any thermal emission from the Earth. It's all in long wavelength portion of the spectrum. So I would like also to discuss a little bit the question of importance of specific part of the spectrum for ocean optics, which is concerned primarily with the study of relatively narrow range of the spectrum from near UV through visible to near infrared, which I've already touched upon yesterday on this topic, but I would like to discuss it a little bit more and support it with a little bit more information. So first of all, let's review again the spectrum of solar radiation, which is a major source of radiation on Earth, and in the context of what we learned about Planck's law and thermal radiation. So what we see here is irradiance plotted versus wavelength. So it's irradiance associated with solar emission outside the Earth atmosphere is this yellow area, or the top of that yellow area is actual values for irradiance of solar radiation at the top of Earth atmosphere. Here you have the gray smooth line is the Planck's black body curve for specific temperature, which is indicated here about 5,800 Kelvin. So you can see it is pretty close to what is being measured at the top of the Earth atmosphere, with some differences here. You can see that in fact the actual solar spectrum shows some features. We'll talk a little bit about this in a moment. And the red portion of this graph illustrates the radiation that reaches the sea level. So you can see the difference between the yellow and the red is the effect of the atmosphere, and you can see some bands, absorption bands here of different atmospheric gases, water vapor, oxygen, CO2 here, and also very strong effect of ozone here in the UV. So you can see ozone is really reducing a lot of short UV radiation that is present outside the Earth atmosphere. So the main point is here again, the peak, the major amount, the major contribution to the solar radiation is associated with the visible part of the spectrum, although we also have a lot of energy within the infrared as well. When we take a closer look just in the near UV to near infrared region, and if we look at the spectrum of irradiance outside the Earth atmosphere, but measured with an instrument that has very, very high spectral resolution, sub-nanometer resolution, we would see something like this solid line. You can see it has a lot of sort of spikes, downward spikes, and superimposed on this graph is several curves, dashed curves, which are again representing the blackbody radiation curves for several temperatures ranging between 5,600 and 5,900 Kelvin. So that again is just a reinforcement of the conclusion that this range of temperature is consistent with temperatures that are expected at the solar photosphere. Now the question is, what is the mechanism for these downward spikes in the solar spectrum outside the Earth atmosphere? They are associated with absorption of radiation, solar radiation by atoms, which are shown here below, which are present within solar photosphere. So for example, we see here around 580 nanometers, the sodium atom has an absorption line, and we can identify this line, this downward spike here in the spectrum, and this location at 580, so that's sodium line. And these absorption lines here within the solar spectrum are referred as Fraunhofer lines. But they can only be measured if we have a very high resolution instrument with sub-nanometer resolution. So typically, most radiometers used in ocean optics would not see this, or radiometers that are being used at the top of Earth atmosphere. Also, if they don't have, they usually don't have this level of, or if they don't have this level of high resolution, we won't see Fraunhofer lines. This table gives us some idea about the distribution of solar energy, and I use here the term solar constant, so I probably should explain it. So the irradiance, the total irradiance integrated over all wavelengths outside the Earth atmosphere is typically referred to as solar spectral constant, but in reality this quantity is not constant. It varies by a fraction of percent on time scale of minutes to decades. But in addition, the solar irradiance reaching the Earth varies also about the mean the mean value of solar constant by almost 50 watts per meter squared over the course of the year, owing to the ellipticity of the Earth orbit around the Sun. So the distance, basically the distance between the Earth and the Sun, is also triggering or causing the variations in the so-called solar constant. But so these values of solar constant here at the bottom of this table is shown in watts per meter square. So integrated across the entire spectrum, it's about 1.4 kilowatt per meter square, or 1,400 watts per meter squared. But as indicated below, this is not constant value, can vary. But this table also shows how shows the contributions of major parts of the spectrum, UV and beyond, near UV visible, near infrared and infrared and beyond, to the total solar constant. So if we just look at the visible spectrum, as we know, it's a very narrow range. We can see the typical values outside the atmosphere is over 500 watts per meter square within the visible, out of 1400 watts per meter square. So that's about 40% of total solar radiation. And if we just look at infrared, it's a little bit over 50% contribution, and UV it's a little below 10%. So this is how the solar energy outside the atmosphere is being distributed between these three major parts of the spectrum: UV, visible, and infrared. So if we now take a closer look at atmospheric transmittance as a function of wavelength, here atmospheric transmittance is plotted wavelengths that extend to 14 microns in linear scale. So visible is right here on the left-hand side, and most of this graph covers infrared. And at the top, we see these arrows that indicate the absorption bands of different atmospheric gases. You can see that atmosphere is quite transparent in the visible, and it's also transparent in some portions of infrared, but it's also totally opaque or partially opaque in other portions of the visible associated with the presence of these atmospheric gases. So the combination of the maximum of solar spectrum in the visible and transparency of atmosphere in the visible results in a significant amount of energy in the visible reaching the ocean surface. And now, when we start looking what's happening when radiation propagates across the air-sea interface and into the water column, now we need also to consider what's going on with interaction of radiation with water molecules. So even assuming that the ocean consists only of water molecules, and that's a nice concept to begin with, we would have to consider the absorption spectrum of water molecules, which is shown here. So, but this graph shows a very broad range. This is a logarithmic scale, many orders of magnitude of wavelength across the electromagnetic spectrum. So the visible band is just this narrow part shown here between these vertical dashed lines. And the vertical axis represents absorption coefficient of water molecules. So you can see also dramatic variation in the magnitude of absorption coefficient. So you can see very deep minimum of molecular absorption by water in the visible, and very sharp increase on both sides of the visible spectrum. In fact, already within the visible, the longer portion of the visible spectrum, from the green through the red, you already see very strong increase of absorption by water molecules. And we will talk a little bit about the mechanisms, what is causing this absorption in a moment. On the left-hand side, you also see very strong absorption into UV, and that's a different mechanism at the atomic level or molecular level on both sides. Here on the left-hand side, these are electronic transitions. On the right-hand side, vibrational transitions within water molecules. So this graph is still a continuation of my thought about, importance of this specific portion of electromagnetic spectrum to our considerations of light in the ocean. And in the top, we have a similar graph to what I've already shown with this yellow-red areas. So I'm not gonna talk about it. So basically, you can see dashed line is the Planck's smooth Planck radiation curve. There is the solid line here that's top of the atmosphere, and there is the line under the shaded area is at the surface of the ocean. And this is the same curve here at the bottom graph. The surface of the ocean is shown here, the top line. And 10 centimeters below the surface, you can see this dotted line. So you can see already a significant drop, reduction of radiation at wavelength longer than 1,300 nanometers or so. And then if we are at 1 meter depth, we we cannot really detect radiation is so low at above 850 or 900 nanometers at 10-meter depth. We're just basically limited to visible radiation. If we go deeper, you can see the process of how the spectrum of radiation is becoming narrower, and it becomes concentrated around a maximum penetration wavelength, and in typical open ocean water that would be around 480 nanometers, but in different water types it can be shifted to longer wavelengths. Okay, so the combination of, again, the combination of solar radiation, which we explained in terms of mechanism of thermal radiation, Planck's law, the properties of the atmosphere, as well as properties of pure ocean water molecules themselves, essentially determine, you know, the importance of the electromagnetic region ranging from near UV to near infrared as the part of the spectrum that we are primarily concerned with. So let's now turn on and move to discussing mechanisms of interaction of light and matter in terms of the other two processes of scattering, so survival of photon, and absorption, which we can also refer to as death of photon. In terms of scattering, there is essentially one fundamental phenomenon of scattering, but in literature it can be confusing to if you're not really familiar with the principles of scattering, with mechanistic principle of scattering, because the terminology in literature is quite diverse. There are terms such as reflection, diffraction, refraction, and me-scattering, or other, you know, names, Rayleigh scattering. We'll talk about that, but essentially there is only one fundamental process of scattering, which we will discuss in a moment, its underlying mechanism. But I will begin with absorption, this graph illustrates the interaction between radiant energy and matter across electromagnetic spectrum. So we are moving from the left-hand side to the right-hand side of the electromagnetic spectrum: gamma rays, X-rays, extreme UV visible, this again narrow range, infrared, microwave. And you have here wavelength of light indicated at below here. And at the top, you see the mechanisms subatomic, or at the level of subatomic scale or atomic scale or molecular scale, of processes that are involved in interaction of light and matter. So if we are in the region of very highly energetic radiation, we have changes in nuclear configuration of within the range of gamma rays, high energy radiation, then X-rays, photoionization, so where electrons can be ejected from atoms, so leave the atom. And if we move to the region of electromagnetic region of interest to us, which is most relevant to us, we start looking at electronic transitions, so the changes in orbital shells, so the distribution of electrons around the nucleus. And then if we move, and that is relevant to UV and visible spectrum. So these energies, the transitions, electronic transitions, are associated with changes in quantized amount of energy within atoms that correspond to energies of photons within UV and visible. And if we go to infrared now, the changes in atomic or molecular vibrations, the changes in internal energy in atomic molecular vibrations correspond to energies of photons within infrared. And if we go further to longer wavelengths, to longer wavelength portion of the spectrum, we start invoking molecular rotations. So in this slide shows is is an attempt to visualize the mechanism of quantized energy states of atoms and molecules, and also is supposed to help us understand what happens when atoms molecule absorbed radiation. So what we see here on the right, on this first graph here, which I'm pointing to at this moment, E1, E2, E3 are represent three electronic levels. E1 is the ground electronic level, E2 higher electronic excitation electronic level, E3 is the even higher electronic excitation level. And so atoms, molecules can absorb quantized amount of radiant energy by moving an electron to another orbital shell or another electronic state transition. So if we, for example, have an atom with these three electronic states, E1, E2, E3, and if the distance between E1 and 2 represents the amount of energy that corresponds to energy of the blue photon, there's a probability that blue photon incident upon the atom will be absorbed. And similarly, you know, we have here a photon, red photon, so it has a lower energy than the blue photon and may correspond to the exact, you know, transition between electronic level E1, E2, and can be absorbed if red photon is incident upon the atom. And we would see it in the spectrum as these two lines. Now, but each electronic state in typical molecules is associated with a series of vibrational or rotational energy states, which are also quantized and can change as a result of absorption of quantized amount of energy. So, for example, this E1, E2, E3 state, each of them has multiple vibrational states, which I'm not sure if this is easily discernible in this slide, but there are thin solid lines that would be vibrational levels, and there are thin dashed lines that would be rotational levels. You can see that these distances between the lines are meant to represent the amount of quantized energy that are required to transition from one level of internal energy to another. So the small distances means very small amount of energy. So that would be long wavelength photon can be absorbed just to move from lower rotational level to higher rotational level, or from lower vibrational level to higher vibrational level. But you can see multiplicity of these vibrational rotational levels associated with each electronic level, to the extent that for many molecules, there are so many of these possibilities, quantized changes within atoms or molecules. Within atoms, maybe not so much, but with molecules, certainly. Simple atoms actually can exhibit these line absorptions, but within molecules, you would have a lot of possibilities and overlapping the scenarios of overlapping vibrational rotation levels between the neighboring electronic levels. So in reality, we can observe nearly continuous or continuous spectrum of absorption, which is shown here. For example, chlorophyll molecule could be seen as having two basic excitation electronic levels and multiple vibrational rotational levels associated with each of these electronic levels, and the highest electronic level corresponds to the absorption of blue light, the lower excited electronic state absorption of red light, but you see multiplicity of these possibilities produce continuous spectrum of absorption. And this is again shown here, the same kind of a model where I have plotted here, I have a graph of ground state, electronic state. So these long lines, maybe it's better, it's clear. Maybe this graph is a little bit more clear. So ground state, electronic energy level 1, so it's the highest electronic level, and this is electronic level 2. So this would correspond to the absorption light, but you can see multiple vibrational levels, multiple rotational levels. And basically, this slide also gives us an idea or provides us insight into the actual amount of energy associated with these different types of internal energies. So electronic energies are on the order of 400 kilojoules per mole. So that corresponds to photons within the region 100 to 1000 nanometers. So that encompass UV, visible, and near infrared, vibrational from about 4 to 40 kilojoules per mole, and that is in the infrared, although some vibrational interactions of vibrational level can, for some molecules, extend into the visible. And rotational energies are smallest, so it's 10 to minus 2, 10 to minus 3 kilojoule per mole, and that corresponds to photons of wavelength higher than 20 microns. And just for comparison, at room temperature, the kinetic energy of translatory motion of atoms or molecules at room temperature is about 4 kilojoules per mole. So it corresponds to this more or less close to the lower boundary within this vibrational energy range. So that explains why the bodies at room temperature, they are practically all within the ground electronic states, but they're continuously can, due to collisions, exchange of energy due to collisions, change vibrational levels. So there can be vibrational excitations and de-excitations with emission of infrared photons at room temperature. This model, the simplified model, which we can use to describe what happens in chlorophyll molecule, is also useful to explain why photons of from different parts of the spectrum play essentially the same role in terms of driving the photosynthetic reaction. Because if the blue photon is being absorbed, which has higher energy than red photon, and the molecule now occurs within this excited electronic energy level 1, that excitation energy is very efficiently dissipated to either into heat, so distribution of energy among the surrounding atoms, molecules, in thermal motion down to the ground state, or to the lower electronic energy level, and very rapidly. So that's, I believe it's like 10 to minus 12 or 14 seconds. The molecule, after being excited to the higher electronic level, would end up in the lower electronic energy level. And then, and that level corresponds to energy of red photon. And this is the excitation energy that, if its fate, can be associated with driving or supporting the process of photosynthesis. So conversion of that radiant energy or excitation energy into the chemical energy in the process, in the reaction of photosynthesis. So regardless of whether higher energy blue photon or red photon is being absorbed, only the excitation energy corresponding to this lower electronic energy level is utilized in process of photosynthesis. And this is why in biology, in research on photosynthesis, it is important to count photons across the visible spectrum rather than express energy in joules per second and per meter square. So the concept of PAR, photosynthetically available radiation, which is expressed in number of quanta per meter square per second, integrated over the visible spectrum, is associated with this mechanism that the energy from the lower electronic level 2 is potentially being utilized to drive the chemical reaction of photosynthesis. But there is also the potential fate of that excitation energy is also twofold. In addition to support of driving photosynthetic reaction, and this excitation energy can be dissipated into heat, so thermal motion, or it can be emitted in the form of photon, red photon, and this is referred to as fluorescence. So you can see that can be a sequence of events where blue photon is being absorbed, and this excitation energy goes down to the lower electronic energy level, and after like 10 to minus 7, 10 to minus 9 seconds, there is a possibility, there is a probability, although it's not very high, about 2-3% typically, that a red photon will be emitted, and this is referred to as fluorescence. So this is an example of inelastic radiative process when you have incident radiation of in this case of blue light, and we have the emission, if you wish, but it's in the red, which is through the process of through the mechanism of fluorescence, and that emission can occur in different directions. So, in a sense, you know, this could be sort of considered as scattering, but in fact, it's the rigorously speaking, this is inelastic radiative process, which is preceded by absorption of photon at shorter wavelength. So that's a very important prerequisite for fluorescence to occur, is absorption, which is associated with specific internal energy level, in this case representing the blue photon. This graph is similar in a sense that it shows also two electronic states associated with energy equivalent to blue and red photons for the model of simplified sort of a model of chlorophyll A molecule. And we have energy here, absorption to blue photon to higher excited states. So these orange lines indicate dissipation into heat, and absorption of red photon to lowest excited state. Fluorescence is indicated here. And here you can see on the right-hand side in the vertical is the axis of wavelength. From the top, we are violet blue towards red, and you can see absorption in the blue, which is associated with higher excited states, absorption in the red with lowest excited states, and there is fluorescence also in the red with a little bit of shift because there are some additional complexities associated with this lowest excited states, which can be in triplet, singlet state, and there are some transitions between the two. So this state actually has some range of energies, and fluorescence occurs generally shifted a little bit with respect to the maximum absorption towards longer wavelengths. So typically the maximum fluorescence is about 683 nanometers, whereas the maximum of chlorophyll, in vivo chlorophyll in plant cells around 672, 75, something like that. And this graph shows, it's just meant to schematically indicate the complexity of different molecules in the ocean. These are just pigments that can be found in plants or phytoplankton cells. So you can see the spectrum of absorption, or just the shape of absorption spectrum, in this dark green line for chlorophyll A molecule we've just discussed, but there are a variety of different pigments, other molecules that can exhibit different spectra and can have maxima and different parts of the spectrum, and also different shapes of absorption spectra. And so this is just an illustration of, you know, potential complexity of variety of absorbing compounds that you can find in seawater. Let's talk a little bit about the most abundant molecule in the ocean, water molecule. And this graph shows the absorption mechanism associated with water molecule vibrations. So you can see that water molecule that consists of oxygen atom and 2 hydrogen atoms, and you can see 3 basic modes of vibrations: symmetric stretch vibrations, asymmetric stretch vibrations, and bending. And these 3 modes of vibrations are associated with absorption of radiation at different wavelengths, so which are shown here. So about 2.6, 2.7, 6, 6.4 microns. So we are now in near infrared or infrared region. And you can also, what's important, that these are just illustrations of very basic modes of vibrations. There are many more possibilities. Higher harmonics or interactions of molecules, water molecules are not isolated, but exist in aggregates. So there are, due to interactions and additional possibilities of vibrations, the spectrum, vibrational absorption spectrum of water is not just consisting of 3 specific lines, but it's much broader. And this is shown here, where you see a very broad spectrum of absorption by water molecules from 10 nanometers to, we're going all the way to 10 millimeters radiation. So here, visible range with the minimum that I've already indicated in one of previous slides, and you can see the increase through the visible, longer portion of the visible spectrum, and these are vibrational absorption vibrational absorption mechanism is responsible for what you see here, this part of the spectrum. And if we move towards shorter wavelengths into the UV, of course, now we have absorption associated with electronic transitions. But again, this is a logarithmic scale, yes, in the vertical axis, so you can see dramatic change in magnitude of absorption as a function of wavelength over a relatively short distance across electromagnetic spectrum with very narrow minimum, which is around 420 nanometers. And this is another schematic illustration of absorption spectra of relatively simple molecules, atmospheric molecules. So you can see CH4 and 2O, oxygen and ozone, CO2, water vapor, and and across the spectrum from UV, visible 0.4, 0.7, so it's right here. You can see, so the vertical axis is essentially absorption. It's not transmittance, but absorption. So if we are here, this white area indicates low absorption, so atmosphere is quite transparent in the visible, and it's also transparent in some portions of near infrared, but it's opaque in the UV owing to the very strong absorption by ozone, primarily by ozone here, causes this strong absorption. In brief, the absorption mechanism is associated with this transitions of internal energy levels, which associated with rotational, vibrational, and electronic changes in internal energy. And now I am going to switch to scattering process and discuss a little bit the underlying mechanism of scattering and some basic features of scattering. You will have an opportunity to have some other lectures. I think Mike will have a lecture, Mike Twardowski, about ocean scattering, so we'll learn a lot about scattering. So here's some basic underlying principles of scattering and mechanism that I will attempt to cover in the remaining slides of this lecture. So scattering by material media, by matter, occurs because of any material medium is inhomogeneous, is heterogeneous in some sense, and that heterogeneities can occur at any scales, at different scales, subatomic scales, scales of atoms, molecules, or aggregates of very many atoms and molecules, which are particles. And so the basic idea is that every medium that contains atoms and molecules will scatter light, which is simply indicated here as the incident light is shown through these horizontal arrows, and we can see scattering in different directions, and we observe scattering at certain angle, and scattering angle is defined between the angle of the beam that didn't undergo scattering and the scattering direction of scattered light. This slide is an attempt to explain how scattering occurs at atomic level, and I will here use a concept of an atom consisting just of two electric charges, negative charge and positive charge, so very simple model. And also I will use a concept that that there is an incident beam of light on these two charges, which is essentially a stream of very many photons which behave like they were dissolved in electromagnetic wave that is characterized by electric field that is fluctuating, like we discussed in using the wave-like concept or classical concept of electromagnetic wave. So first, let's define the quantity that is referred to as dipole moment, P, which is a product of the magnitude of the charge times the distance or separation between the positive and negative charge. So that's the dipole moment. And here we have a graph that indicates that, okay, we have a positive charge here in the center and the cloud of electron. So the electron can be anywhere within the space here. And we are subjecting this the system of two charges to incident radiation, which is, as I indicated, associated with time-varying electric field. So the time-varying electric field will exert forces on these charges. So these charges will, in other words, they will feel the incident light or the time-varying electric field of incident light, and they will respond accordingly to the strength of the electric field and fluctuations in this electric field. And electrons will basically be more susceptible to respond to the incident electric field. And so you can see here on the right-hand side that at any instant, the electrons and the cloud of electrons can be sort of shifted relative to the position of the positive charge. And as this incident electric field is fluctuating, this scenario will also fluctuate. So basically, at any instant, we can quantify the so-called instantaneous induced dipole moment, which is quantified as the product of strength of the incident electric field times this quantity alpha, which is called polarizability. It's the quantity that is associated with the chemical makeup, or if you wish, of this specific atom or substance that we are considering. And this polarizability essentially tells us how the extent to which the electrons or the discharges are willing to oscillate or separate from each other in response to a given incident electric field. So if you have different chemical substances, they will exhibit different polarizability, and this polarizability is actually also connected or associated with the refractive index of chemical substance. So that's another interesting twist here. But the main point is that in response to the incident electric field, which is time varying, the induced dipole moment, which also fluctuate, so the charges will also move, and accelerated charges will produce time-varying electric field, and time-varying electric field, according to classical theory, electromagnetic theory, produces time-varying magnetic field. So we are essentially producing a secondary field, which is exactly what we refer to as scattered field. So So this model of an oscillating dipole is here being used as to explain the mechanism of light scattering. So oscillating dipole is producing its own electromagnetic field, which propagates in different direction, and it manifests itself as scattering. So here I also have some text. Polarizability is the relative tendency of a charge distribution, like the electron cloud of a molecule, to be distorted from its normal shape by an external electric field. So that's the incident light, like the one in an electromagnetic wave. So this is something that I typically like to use the model of oscillating dipole as an explanation, as intuitive explanation of why light is being scattered upon interaction with matter, which consists of positive and negative charges. Now, these interactions, scattering interactions, can be elastic and inelastic. So I'd like to briefly define these two concepts. Elastic scattering is associated with no change in energy of or wavelength of scattered light if compared to the wavelength of incident light, or no change in energy of photons, scattered photons, compared to energy of incident photons. This graph has this bunch of horizontal lines, so let us assume that these horizontal lines here, 0, 1, 2, 3, 4, these are the lines of the ground electronic state, but different lines represent different vibrational energy states within the ground electronic state. The lines here up there they are not supposed to represent any specific quantized internal energy levels of atoms. So this is not a like excited electronic state. It's just meant for illustrative purposes to show some virtual energy states, just to make simpler the graphical representation of these arrows, to explain what happens when we have, for example, blue photon incident upon the system of two charges, and blue photon is being scattered, and the atom still remains in exactly the same internal energy state. So it is within the same state, electronic state, and the same vibrational state. Now, inelastic scattering occurs when there is a change in wavelength of scattered light compared to the incident light, and the inelastic scattering process is referred to as Raman scattering. It has been discovered by Raman, Indian physicist, in 1920s. And there are two ways of the Raman scattering can manifest itself. First is that the incident photon has a higher energy than the scattered photon, which is illustrated here. So, for example, blue arrow represents incident photon on an atom or molecule, and the scattered photon has somewhat longer wavelength, but to satisfy the conservation of energy, the atom, upon this interaction, increases its internal energy by a certain amount associated with increased internal vibrational energy state. So that's this example is of so-called Stokes-Raman scattering, where longer wavelength is being scattered compared to the incident wavelength. And the opposite can also happen, anti-Stokes-Raman scattering, where the Raman scattered photons has a shorter wavelength than the incident photon. However, this phenomenon does not really occur in the ocean. Raman scattering, by the way, is a very common phenomenon produced by water molecules. So water molecules, of course, scatter elastically, and that is often referred for molecular scattering as Rayleigh scattering. But water molecules can also produce Raman scattering, the Stokes-Raman scattering specifically. And this process can occur continuously across the spectrum, and the shift here in wavelength between incident photon and wavelength of scattered Raman scattered photons is relatively small, because these vibrational energy, differences in vibrational energies are relatively low. So these shifts are on the order of tens of dozens of nanometers, but the Raman scattering by water molecules occurs across the spectrum, and it's extremely important process within the ocean that I'm sure you will learn more about during the coming days. So here this slide indicates elastic scattering and elastic scattering processes and fluorescence, which are all relevant to ocean optics. So imagine a sample of water illuminating by a beam of light of certain wavelength. And so what you can see, portion of energy can be transmitted. Some energy can be absorbed, which is not visualized explicitly here. And some of the energy can be elastically scattered, so no change in wavelength. There's a potential for fluorescence depending on compounds here, such as chlorophyll can produce fluorescence, and also Raman scattering, Stokes scattering, because anti-Stokes doesn't occur at under environmental conditions, typical environmental conditions in the ocean. Okay, so now I will characterize several basic features of scattering as a function of the size of particle. So imagine that we have a very small object, such as molecule or very small particle, which by small I mean that is much smaller than the wavelength of light, at least 10 times smaller than the wavelength of light. So if we again think in terms of classical electromagnetic theory, so we can visualize here an electric field and a small molecule or small particle here embedded within this electromagnetic field. And you can see that at any instant, this molecule, which we here assume consists of positive and negative charge, is experiencing a specific phase of the incident field. So that's a relatively simple scenario. So as the times go on, this molecule will experience different phases and different magnitude and the phase of the incident field. In contrast, the scenario becomes much more complicated if we have much larger object, larger particle here shown, a particle that is in size comparable to light wavelength. So you can see that different portions of that particle, that object, is experiencing at any instant of time, is experiencing different electric fields. So these charges, you can imagine there are very many pairs of positive and negative charges distributed within this particle, and each of these pairs of charges or dipoles, which then produce scattered field, they experience different incident fields. So you would expect that the scattered field produced by this collection of dipoles experiencing at any instant of time different incident electric fields will produce much more complex scattered field than compared to the situation where a very small particle or molecule is being considered. And this graph explains, using this graph, I will explain a few concepts or will try to explain qualitatively why scattering depends strongly on the angle, on scattering by any object, arbitrary object, depends on scattering angle, why it depends on the size and shape of the object or its chemical makeup or composition. So imagine here that we have a particle and we can conceptually subdivide it to very many dipoles, so pairs of positive and negative charges. We illuminate this particle with incident electric field. Each of these dipoles experience a certain electric field, and it oscillates and produces a scattered field in different directions. Now, if we just observe radiation, scattered radiations with a detector at a specific scattering angle, the net result will be superposition of waves, scattered wave fields produced by each of these dipoles with due account for phase differences between each contribution. And these dipoles are small and non-random, so scattered wavelengths have non-random relative phases in the direction of interest. So the total scattered intensity here at the detector is obtained by superposition of scattered wavelengths where the phase differences must be accounted for. And this kind of scenario, when we have to account for phase differences between different sources, in this case multiple dipoles embedded within a single scattering object, is referred to as coherent scattering. Now, imagine that we increase the size of the object, so we have very many more dipoles, so you would expect many more these basic entities or sources of scattered radiation. So if we increase the size of the object, you expect to increase the scattered intensity. Now, if you change the shape of the particle, but keep the size more or less the same, you would also expect the change of the intensity at any given scattering angle, because you will change the relationship, the phase relationship between these different contributions coming from individual dipoles. Also, if we change the chemical composition, in other words, we change atoms, molecules that form these dipoles, they will have different polarizability, different refractive index, so they will also produce different scattering intensity. And finally, if we move the detector all around and change the for any scenario, for any fixed particle, if we move this detector as a function of angle, you're gonna see the differences in scattered intensity simply because the contributions of these the interference pattern, if you wish, because we have to. It's essentially what we are doing here with coherent scattering. We are looking at the interference patterns coming from contributions from all these individual dipoles. So this interference pattern will be changing, will be either more constructive, less destructive as a function of angle. So we'd expect strong dependence on scattering angle as well. So I hope that at least qualitatively, this kind of model explains, something that you will be learning a lot during this course, how complicated or how complex scattering by marine particles can be. And it's sort of, we can trace it back to these mechanisms, which are so sensitive to size, shape, internal structure, and chemical composition, and also, of course, angular aspect is also very important. So in terms of computations, I want to briefly so of course, in terms of scattering, you have there are experimental approaches and there are also theoretical approaches. I'd like to briefly mention some theoretical approaches for computing light scattering. First approach is the approximation, Rayleigh scattering approximation, which applies to very small scattering objects, much smaller than light wavelengths. Oftentimes, the Rayleigh scattering refers to molecular scattering, but can also be a relatively good approximation for very, very small particles, smaller than at least 10 times smaller than light wavelength. So Rayleigh developed this approximation to using the model of oscillating dipole, essentially, and he also explained the blue color of the sky. I will talk a little bit in a moment about this, the wavelength dependence of Rayleigh scattering. This happened at the end of 19th century, the work by Lord Rayleigh. At the beginning of 20th century, Gustav Mie, a German scientist, physicist, obtained a complete analytical solutions of Maxwell equations for scattering of electromagnetic radiation by spherical homogeneous particles of arbitrary size, arbitrary refractive index. But the important thing is that it's a sphere, but it's internally uniform. Since then, theoretical extensions of Mie theory or Mie solutions were developed for more complex shapes, such as coated, layered spheres, cylinders, and spheroids. But basically, these theories, these theoretical approaches can be very useful, can provide some guidance to us of what to expect in terms of scattering by different objects if you change size, if you change refractive index. However, they are all, regardless of whether it's coated layer sphere or cylinders, there are all approximations, oftentimes not suitable to predict actual scattering in the ocean for the most part, because as we know, the natural particles in the ocean consist of very many shapes, very many sizes, types, and are much more complicated optically than these theories assume. But these theories have been used, and one of the most advanced theoretical approaches to calculate scattering is the so-called discrete dipole approximation, which is a method for computing scattering essentially by arbitrary particles, arbitrary shape, and even arbitrary internal composition, because this approach, DDA approach, discrete dipole approximation, assumes that a particle, here is shown like a sphere, but we could have any other shape. Doesn't have to be a regular shape, it could be irregular shape, is divided in very many dipoles. Each dipole is given a polarizability. So if you give different polarizability to different dipoles, you would invoke that the internally particle is non-uniform. And then you can, with very complicated math and codes, you can compute the scattering pattern. This is computationally very demanding process, and in optical oceanography, it has been applied just in a few cases, scenarios, as far as I know. For routine applications to actual particles that we find in seawater, this discrete dipole approximation is not really well suited. Again, we do not have a priori knowledge about thousands of types of particles to model them in terms of internal structures and assigning to millions of dipoles within a particle different polarizabilities and so on and so forth. So this is not really a practical approach for actual particles in the ocean. And on another side of the spectrum of complexity, this is a simple approach that has been used historically quite a bit, geometrical optics approximation for light scattering, which works quite okay, but only for particles larger than light wavelength and much larger than light wavelength. So this is basically a ray tracing method where you can trace the behavior or the fate of light represented by individual rays as it interacts with particle. Here is the uniform sphere, and you can assign certain refractive index to it, so you can look into reflections, external reflections, refraction and internal reflections and refractions, and also if you add diffraction to it, you can basically predict the scattering pattern for particles that are much larger than light wavelength, about 10 times larger. It can work well. And this approximation was shown to be for spherical uniform spheres to agree quite well with rigorous misscattering calculations. And similarly, the Rayleigh scattering for molecular scattering or very small particles also was shown to agree well with rigorous misscattering calculations. And there are many regimes of particle scattering depending on the particle size, refractive index, light wavelength. So there is the terminology, as I mentioned, can be confusing, but there are countless observable effects of light scattering. Although all scattering phenomena are fundamentally the same, and I like to really refer you to this oscillating dipole mechanisms in that sense. But here you have graph where different terms are being used for scattering within different domains of refractive index and particle size relative to wavelength. In terms of particle size, it's important to note for scattering that geometric particle size is not as important when you consider scattering by particles But what's important is the particle size parameter, in other words, geometric size relative to light wavelength. So this particle size parameter, which is called, use the symbol alpha or x, is basically quantified as the ratio of 2 pi r, where r is the radius of particle over lambda, or pi diameter of particles d over lambda. So you can see the geometric size relative to wavelengths is what really is important in consideration of light scattering by particles of different sizes. For Rayleigh scattering approximation, this particle size parameter is much smaller than 1. For geometrical optics approximation, this parameter is much larger than 1. Sorry, much smaller than 1 for Rayleigh and much larger for geometric. You can see here these different terms: Rayleigh scattering, Rayleigh guns, geometrical optics, or totally reflecting optics, reflecting objects. But essentially, again, scattering phenomena are fundamentally the same, regardless of how you call them. This is a little bit easier to interpret because I graphed here particle size, geometric size, from atomic sizes through nanoparticles here, less than 100 nanometers. These are 1 micron particles, very abundant in the ocean. And as we go to larger sizes, less and less abundant particles in the ocean as we go to centimeter-sized particles. But this is basically the range of from molecular sizes to large particles that covers particles that are encountered in seawater. And on the horizontal axis, you can see the wavelength of light, and the visible light is right here. So the Rayleigh scattering is in the visible region is consistent with these very small sizes. Scattering is applicable to these sizes from dozens of nanometers to hundreds of microns, and geometric optics approximation could be applicable to particles above, let's say, 10 microns or so and above. Let's see, I'm practically, I have probably a few slides. So very quickly, the angular distribution of scattering is shown here through this polar region. So on the top, we have molecular scattering, Rayleigh scattering. When we have incident unpolarized beam of light, it is being scattered in different directions symmetrically with the same amount of light in forward directions and same amount in backward directions, and less light at 90 degrees. And this is the angular dependence is shown through this cosine squared angle of scattering. Then if we increase the size of particles relative to wavelength, we immediately start seeing a lot more forward scattering compared to backward scattering. If we have very large particles, we have very elongated angular distribution of light, a lot of forward light. But if you have a single particle, you can see also, if you look at different angles, you can see complicated patterns. So minimum and some angles, maximum, some other scattering angles, minimum, maximum. So this is basically destructive and constructive interference associated with this coherent scattering produced by different dipoles embedded within a single particle. I will skip this one, and very quickly, a couple of comments about scattering as a function of wavelength. So molecular scattering is very sensitive to light wavelength. Shorter wavelengths are scattered a lot more strongly than longer wavelengths, and molecular scattering characterized by lambda to -4. And for water molecules, that dependence is even stronger with the exponent about -4.3. So basically, if you plot this function, power function, you can see here dependence of scattered intensity, this function of wavelength. UV is scattered much more strongly than violet, blue, green, yellow, and red. And that explains the color of blue skies, which is shown here as well. And if you look at pictures like this and the sun at the sunset and away from it, you can see blue sky. And if you look towards the sun, you can see red colors start to predominate because path length between the sun disk and observer is very long within the atmosphere. So along the long path lengths, the blue photons are scattered by molecules away from the direction of observation. So the light, when you look towards the sun at the sunset, this direct sunlight becomes and is sort of relatively enriched at longer wavelengths because blue photons have been scattered by molecules. On the right-hand side, you also show another visualization or representation of wavelength dependence of scattering. When we look at clouds, consist of particles that are relatively large, comparable to light wavelength or larger, and you can see white or grayish color, so that indicates that scattering by larger objects are weakly sensitive to light wavelength or weakly dependent to light wavelength compared with molecular scattering. And I also, because this course, during this 2-week course, you will have quite a lot of information and material and lectures and sessions devoted to ocean color and remote sensing. And I would like to bring here to your attention the work conducted by Raman. So the same physicist, Indian physicist who discovered Raman scattering I discussed, but he also published in 1922 paper on the molecular scattering of light in water and the color of the sea. He actually was on the ocean voyage from India to Great Britain, and it took quite a long time at the time, and so he had time to observe, make a lot of observation. And here's a quote from his work: "In the opinion of the writer, it would make for progress to recognize that the observed color of the sea is primarily due to water itself, and that suspended matter is to be regarded as a disturbing factor of which the effect requires to be assessed in each individual case." So in fact, Raman was correctly indicated the source or the explanation of the color, intrinsic color of the ocean, which before his work was largely associated with reflection of skylight from the ocean, that the blue sky of the ocean water was associated mostly with reflection of blue skylight. But Raman correctly observed that there's intrinsic color of the sea, which is associated to the interactions with water molecules themselves. So of course, water molecules have minimum absorption in the blue, high absorption in the red, so they contribute to the blue color, but also they have a very strong scattering in the blue, which reinforces the blue color of clear water. But he also, very importantly, recognized the fact that there are a lot of other things, constituents in seawater, which can change the color of the ocean, and that causes the problem, a very complex and has to be assessed and studied in each individual case. So I will stop